Okay, good morning. We'll do a design on a beam which is subjected to torsion. Okay, yesterday we saw the provisions relating to torsion, so we'll do a problem on that now. The typical example that I can give is if you have a beam on the, if you have a floor system and you have a beam on the edge of the floor. Okay, so that is the most typical example that I can give. Okay, so for example, if you have a floor system like this. Okay, so there's a beam here, there's a beam here. Okay, another beam and another beam. Okay, so when you look at such a floor system, there are loads, there is some dead load and live load on all these parts of the floor. Okay, so because of this loads, what will usually happen is if you take these beams, they will have a, because of the load on this side, they have a moment acting this way, and because of the load on this part of the beam, they have a moment acting this way. Okay, and as long as this span is more or less equal, okay, as long as these spans are more or less equal, then these two will actually cancel out. Okay, and you say that this particular beam will not have any torsion, and so on. This beam also will not have much torsion. But when you come to the exterior beams, these will have some torsion because there's nothing on the other side to balance them out. So this is a typical case where you have where you could have torsion. Okay, so let us look at one such beam. Okay, let us consider it as a rectangular beam itself rather than considering it as a flanged beam. Okay, so let us say that we have such a floor system here. Okay, and let me just give some random dimensions to this. Probably this support is 300, and this is maybe if it is 5 meters apart, then this will be about 2.5 meters. Okay, I'll give dead load and live load as well. Dead load I can give as about 4 or a 7. It will make it quite big. And live load I can say is about 4. Quite heavy loads. Deliberately I'm giving some heavy loads. Okay. So this is the beam that is we are going to design for torsion. Okay. So the solution structure is very simple. It's very similar to what you have all done until now. But anyway, nonetheless, let us go step by step. Let us also assume it is M30 and Fe500 steel. Okay, M30 concrete and Fe500 steel we can assume. So first thing that we can assume is this this span I have not given. No, this span is about maybe I can give about 6 meters. It is 6 meters circle. Okay, let me not go into too much detail of too many things. Let me say that the effective span itself is 6 meters. Okay, so effective span itself I'm giving as 6 meters. I'm not giving the center to center span. I'm just saying the effective span itself is about 6 meters. Okay, so if the effective span is 6 meters, then, and this is of course let me say simply supported, then what do you think should be my depth approximately? If effective span is 6 meters, so you have the conditions L by D ratios. So what is the L by D ratio for a simply supported beam?
20.
20. Okay, so L by D is 20, meaning that my D should be approximately 6000 by 20, which is about 300 mm, based on serviceability conditions. But if I give 300, I looking at 300 itself, I know it's not too big. So let me make it about. Let me keep about. Let me try with 450 mm. Okay, let me try with 450 mm. So of course, if I want, I can also find the effective weight of this particular self weight of this beam. I can find. It's nothing but 25 times. What is this? So this is 300 breadth, and if this is mean, then depth will be about 500 overall depth. Okay, so this is self weight. Then dead load you have. So dead load is 7. This width I've taken as 2.5. So that will be about 7 into 2.5, and live load again is 4 into 2.5. Okay, so the total unfactored load will be this much. So unfactored load equals how much? So just multiply all these, add all of them, give me one by one. What is the first one? Self weight of the beam?
3.75.
3.75, sorry, okay. Dead load?
17.5.
17.5, no?
This is 17.5, 10.
10. So total is how much? This is about 10, 27.5, 31.25, yeah.
This is 31.
Okay, so this is the unfactored load, and factored load will be 1.5 times this. Which will be about 1.5, no, something close to 45, no? 40, 48, how much?
46.87.
How much? 40?
6.87.
46.87.
5. 875.
Kilonewton per meter. Actually, you know, load is still slow. Anyway, so this is the factored load. From this, I can proceed and find what the moment and shear forces are. Okay, moment is simple. Okay, you know that it's moment we call it as mu is WL square by 8. W is this. L is I've given the effective span is 6 meters. Okay, so 46.875 into everything is in kilonewton and meters, so 46.875 into 6 square by 8, how much?
To 10.9375.
To
10.9375.
to 10.9, okay, fine. Okay, so this is the moment. Moment U caused only by the load. Similarly, shear, of course, I'll take it at D from the face of the support. Support I can probably assume 300 mm. Okay, so which means that if this effective span I said is 6 meters, so this I took as 6 meters, and if I take the support is 300 mm, so this will be 150. And depth D is effective depth I've assumed is 450, no? 450. That's what I've assumed. So anyway, so 450, 150. So this will be 450. So the remaining part will be nothing but. So here to here is 3. That's the middle, and therefore here 150, another 50. So this will be 2.4 meters. Okay. Anyway, so for 6 meters it is WL by 2. Okay, that is at the support. The shear will be WL by 2. So the remaining part is this remaining whatever we have. We just have to subtract that. So that will be the W by 2 minus W into how much is this 600? Okay. So just so anyway, everything you know, W you know, L you know, X is we just calculated it to be 0.6 from the this point the point from where you take the effective span. From that point, it is at 600 mm. Okay, so just find this out. How much is the VU that you get? How much is it? W into 6 by 46.875 into 6 by 2 minus 46.875 into 0.6 by 2. So this will be about close to 150, and then 150 minus some small number. How much do you get? .875 into 6 by 2 minus 46.875 into 0.6 by 2. Secret, how much do you get? Please tell me, no? Do you get about 127? Hello?
Sir, but sir, by using the triangle, I'm getting 112, sir, 112.5.
112.
Sir, like if we draw the triangle, like how we
Okay.
did two classes before, like I'm getting like
Yeah.
112.5.
So at the end it will be 46.875 into 3. Okay, 140.625 into 2.4 by 3. Oh, sorry, correct. This 2 will not be there. It's WX only now. This 2 will not be there, sorry. It's not by 2. Okay, now you'll get 46.875 into 3 minus 46.875 into 0.6. Then you get 112.5. Okay, yeah, that's correct. Okay, so now what you should remember is these two are just the actual moment and actual shear. Okay, coming from the vertical loading. But we also have a torsion. We have not yet calculated anything about this particular torsion. Okay. Now, what causes this torsion? Okay, what causes this torsion is only this. Only these loads cause the torsion. These two, which are present outside this this 7 and 4 kilonewton per meter square, which is present over this 2.5 meters of width. That is the one which is going to cause the torsion. Okay, so what I say is, we'll do the torsion calculation. Okay. Okay, one thing you should remember is torsion. This is how the torsion will act. So if you have the beam, so on this side you have the slab which is having the loading. Okay, so therefore every bit of this beam will be subjected to a torsion. Every meter of this beam, every unit width of the beam will be subjected to a torsion caused by the loads on this. Okay, all these loads, they are going to cause the torsion on this particular beam. Okay, so the load causing the torsion is, okay, total is a factor load which causes torsion is, we have 7 and 4, so total is 11. Okay, so 11 into 1.5. How much is 11 into 1.5? How many kilonewton per meter square? Okay, this much kilonewton per meter square, and it acts for a width of 2.5 meters. Okay, so therefore torsion per meter, okay, is 16.5 per meter of beam. Okay, 16.5 into 2.5. How much? This is about 50 or something, close to 50 you get. Not 50, you get about 40. Yeah. How much is this?
41.25
kilonewton meter per meter, meaning that this torsion which you have, see, which you have over here, which this whole torsion is 41.25 kilonewton meter per meter. Okay, now we have moment, we have shear, we have the torsion. So before we find the effective depth of the beam which is required, we have to find the equivalent moment and equivalent shear. So the equivalent moment. Okay, so this formula is present in your IS 456 code book. We saw this formula yesterday. It is nothing but MD equals TU into. So this is TU. MP equals TU into 1 plus capital D by B divided by 1.7. Okay, keep everything in kilonewton meter itself. Okay, this torsion is 41.25. 1 plus D I said is 0.5. The full, I mean, we don't know yet, we're going to find the depth, but I think capital D 0.5 should be sufficient. So divided by breadth is 0.3 by 1.7. So how much is this? How much is the moment, the bending moment effect by the torsion? How much is it?
64.7.
64.75. Okay. Others also get 64.75.
64.705.
705. I'll make it as 71. Okay. So therefore, total moment is nothing but mu plus mt. Okay. So this is the maximum. You can also do mu minus mt for the, for example, for the bottom, if you do mu plus mt, for the top it becomes mu minus mt. But anyway, since we are going to design only for the maximum, let us just carry out mu plus mt. So mu we found was 210.9. MT is 64.71. So what is the total?
$275.64.
270.
5.64.
Okay, so you have a reasonably good effect of torsion from. So the moment which you originally would have decided for is 200, but because of the torsion, you need to actually take 275. Similarly for the shear. Okay, this we call as a VT. Okay, this is also present in your codebook, the section of torsion. If you look, you will find the formula. It's V plus 1.6 TU by V. This is 1.6 TU by V. 1.6 TU by V. 1.6 into TU is 41.25. B is 0.3 to breadth of your beam. So how much is this?
So like shouldn't the unit of torsion be meter per meter square?
Which one?
Like the unit of torsion, like 16.5 kilonewton per meter square into 2.5 meters. So it will like 41.25 kilonewton meter per meter square.
See this 16.25 is multiplied by 2.5, which becomes per meter, no? And then you multiply that. Okay, 1 minute. 2.5 meters. Okay, yeah, 1 meter per meter square na varakudadu. Ayo, sorry for one mistake. So, actually, there should be another into 2.5. See, this is the case, no? Sorry. So this is actually W into L. So that's what I've done here. I should also do another for getting the moment. I forgot to do that. Oh my god. Okay, so some things are going to change. See, it's basically cantilever moment formula, nothing else. Okay, so WL into L by WL is only shear. WL into L by 2 only will give you the moment. WL square by 2. So this is for this it will be 41.25. For this it will be another. So this will be something. Similarly here, it is not 41.25, it's something else. This will be something else. And so will this also be something else.
1.56.
Yeah, we'll come to it in just a minute. Let me just erase this. Good that you pointed that out, otherwise you would have proceeded to complete the whole problem wrong. So how much was this?
51.56.
51,
0.56.
Okay, so this is 51.56 kilonewton meter per meter. And this will be 51.56 here. And this will be, okay, so you need to tell me what this is before I can get this.
$80.87.
80.87. So this will be about 280 point something, 200 and how much?
291.7.
Okay, and VT? You'll get a relatively big number, I suppose.
So 274.98.
Quite a big share. Okay, 274.58.
So 98.
Okay, some 275. Let me just keep it as 2.5. This decimal point is not going to affect me in any way. 275. So now my total shear equals the original shear was 112.5 plus 275. You have binomial shear. So this is 380. Correct? I may need a much deeper beam, I suppose. Pilot may not be sufficient. Let's see. Okay, so now I'll decide my beam MU limit as I usually do. This is for Fe 500 steel. So 0.46 FCK BD square. So this should be equal to 291.7. So giving me D equals FCK is M30. Okay, M30. The B is
So it should
300.
be 0.136.
Point?
0.133.
Ah, 0.133. 133.
Yes,
133.
sir, 133.
Sorry, I gave the FCK formula by mistake. Okay, some people are attentive. That's good. 500 square. No, sorry, 450 square. Effective depth. No. Effective depth is 450, not 500. Full depth only is 500. Oh, yeah. Sorry, I'm messing up things. D is what you have to find. We need to check whether 450 is okay. Yeah, so how much do you get D? Find out D and let's see, what comes. If it's 450 or more than 450, what we need, we'll see. How much is D?
So it's coming around
493.6.
493.
493. Okay, so we need a bigger 493 mm. So let's make it quite big. Let's provide the depth because my shear is quite big. So I'm going to actually give quite a big beam. Okay, have a really big shear here, 387 kilonewtons. It's actually a really large shear to have. So instead of 493, I'm going to provide I'm going to put a pretty big beam. I'm going to say that provide the effective depth of, let me say, just to be safe, let me say 650 mm. Okay, meaning that total depth D will be about 700 mm then. So right now, because we have actually revised our depth by quite a large amount, because we revised it by quite a large amount, I want to actually just check what change I get over here. Okay, I want to see whether this is going to be too much different. So if this becomes 0.7, what do the remaining things become? So this is a problem in torsion where you may have a depth and then you will proceed to find the moment. Then when you find it, you may find that the depth increases. So in such a case, you will have to revise it. This is something we cannot avoid. How much do you get?
So like since the load, since the depth has been changed, so the load won't be changed.
Self weight will change a little bit, but that will not be too much. It's a minor fraction of what you will get due to this change. So you need not worry about that too much. Self weight will marginally increase, but compared to everything else, that is marginal. So you can forget about it.
One not 1.1.
Meaning this is about 310 kN. Okay. For equivalent shear, no problem because D does not appear. So I need not worry about changing the shear value. So this is 310. This was 291. I suppose, see, what I required was 493. I've given 650. So even if I make this 310, this will be definitely sufficient. If you want, you can check it. But I know by just looking at this will be sufficient for 310 kilonewton meter also. Okay, so I'll proceed with this, and of course we'll also provide the required tension steel. $50 FCK by FI or FI by FCK? What is it? Anyone remembers?
FCK by FI.
1 minus root of 1 minus 4.598 mu by I hope the formula is correct. So FCK is 30. This is 500. Mu is 310. B is 300. This is actually we given 650. So after this, there's only 1 or 2 more steps. It's almost over.
So 0.63%.
Okay, reasonably good value, 0.635.
So
this
0.63. 0.63.
0.63 alone, not 5. Okay, pretty good, decent value, 0.63%. So AST equals 0.63, 300 into 650 by 100. So how much is this? This comes about comes about 1,229, I think. Yes. Do you get 1,229?
Yes, sir.
Okay, so this is a good number. So I'll give 4 numbers of 20 diameter bars. This will correspond to about AST equals 1256 mm square. Okay, so corresponding actual PT will be. Why I need the actual PT now is because I'm going to find out. I need to find tau c and all those things. Okay, so that's the reason that I'm actually doing this. PT actual is 1256 divided by 300 into 650. Okay, about 0.645. Okay. Now, so the tension reinforcement is over. Now, when going to the shear reinforcement, we proceed as we always do for shear. Okay, so shear reinforcement. So the first thing that you will look at is you will look at the table for shear, the same table number 19. Okay, but before that, let me check my actual tau v. My actual shear is 387.5, really big value. Okay, into 10 power 3 divided by 300 into 60. Now I better hope that it comes lesser than tau c max. If it does not come lesser than tau c max, then I have to increase the depth further. Okay, so I pray to God that it comes lesser than that. And God is correct. Okay, so this comes about 1.99 Newton per mm square. Okay, now you compare this tau v with table number 20 of your IS 456. There, for M30, tau c max is 3.5. Okay, and thankfully this tau v is lesser than tau c max, which equals 3.5 Newton per mm square. Okay, so because of this, I'm saved. I don't need to increase the depth of the beam any further. Okay, so this is the reason that I had actually increased the depth by quite a large amount, because when I saw this shear force, I knew that it's quite big, and I may be at a risk if I just restrict with 500 or whatever overall depth. Okay, so sometimes when you look at a shear force or a bending moment, you may want to predict initially itself, like whether to give much more depth or retain it at what you actually calculated. Then I also want to find what is the total shear resisted by concrete alone. So I use table 19 for that. In table 19, I have between 0.5 and 0.75. Okay, so 0.5. So for PT 0.5, I have tau c is for M30 0.5. Okay, so this is also 0.5, this is also 0.5. And for PET 0.75, I get tau c equals 0.59. Okay, this is 0.644, which is about it's not exactly half, it's a little more than half. Okay, so I'll probably say that my tau c will be close to 0.56. I think it will be something close to 0.55%. Sorry, per Newton per mm square. For PT equals, okay, if you want, you can calculate the exact. You can do interpolation, you can calculate exactly what it is for 0.644. I didn't want to waste time doing that, so I just guessed that it will be something close to 0.55 and I've given that. Okay, so therefore the shear resisted by my concrete will be 0.55 into 300 into 650. How much is this? So this is the limit. This is
So
actual,
107.25 kilometer.
how much?
107.25.
107 kilonewtons.
107.25 kilometer.
Okay, don't bother too much about decimals. So this is the actual full shear force. This is the limit. Full is lesser than the limit, so no problem. This is the shear force resisted by concrete and tension reinforcement. So what should be resisted by this shear reinforcement? Resisted by, or to be resisted by shear reinforcement is nothing but the total is 387.5 minus 107.2. So this is about 280.3 kilonewtons need to be resisted by my shear reinforcement. So now for this we have a formula. This is not the same formula which we used only for shear. For torsion we have to use a formula which is given in the torsion part. Okay, so that is like this. Okay, ASV equals, so this is given in class 41.4.3. TUSV by V1 D1 TU into SV by B1 D1 into 0.87 FY. Okay, D1 is nothing but the actual D which you have, nothing different than that. Okay. You didn't got it. And VUSV, that's VUSV divided by, so if you have a code book, you can have a look at it, 2.5 D1 into 0.87 Fy. So now before this I need to assume what are all the things that I have. So if this is my beam, I need to find out a few things. I need to find out B1 D1. So assume that, so bottom is 4 number of some bars I'm given. Top assume that I'm giving something to hang the bars. And my stirrups come like this. Okay, so D1 is this. So this is D1 and this is B1. This is also B1. Basically the stirrup is a rectangle, you know. The center to center distance of that rectangle is B1 and D1. Okay, that's what they are. So I assume 50 mm clear cover is here, this side and this side. So therefore this will be 400. This will be 200 if I assume 50 as clear cover. Okay, so 400 and 200 are the values of B1 and D1. I will assume something for the, I will assume, so this is quite a large shear, so I'm going to go ahead and assume maybe 12 mm bars. Okay, 2 length. So what then means ASP will be 2 times 113. One single 12 mm bar is 113. So this will be 226 mm square. And I'm going to make sure that they are actually also FE 500. Okay, because quite a big shear. Let me have 500 steel itself, and let me have a big. Let me actually make it 10. Let me see if 10 works. Otherwise, I'll go to 12.
So the overall depth is 700, right? So with 700
oh,
minus
right. Thank you, sir. Overall depth is 700. No? Okay. I was remembering 500 itself. Sorry. Then that is 600 then. So 10 mm was 78, 156. Okay. So I can just rearrange this and say, so just proceed to start calculating it. So I can just rearrange this equation. Okay, so I have just taken SV out common so that you can easily find them out. Other things I just retained inside the bracket. So this is 156. TU was no. TU was 51.56. VU, be careful, don't take V total and moment total. Take TU and VU only. TU is this, VU is this 112.5. Don't take the full overall total. Okay, don't do that. Okay, for finding for finding the reinforcement, take TU and VU. Do not take what you took over here. Okay, don't take the full shear plus torsion shear. Okay, don't take that one. Take TU and VU only. Okay. So VU is 112.5. Okay, so be careful about that. 200, 600, FY is 500. This is 600, and again this is 500. Okay, so let's make it fast. 51.56 divided by 200 into 600 into 0.87. Set up a new 100.583 divided by 2.5 into 600 into 0.87 into 500. 0.172. So 156. I'm getting AS spacing is approximately 135 or something like that. Let's check whether you get
134.46.
Yeah, so something close to that. So just check whether you get it. Just make substitutions, you'll get something like this. So SV comes about 135.41. This is the calculated. So you also have some restrictions on what the spacing can be. So these restrictions are given in class number 26.5.1.7. Okay. 26.5.1.7. You look at this class, you have restrictions on the maximum spacing that you can give. So the maximum say that this or x1, okay, x1 which is equal to x1 is nothing but short dimension of the stirrup. So short dimension of the stirrup, it's basically this b1. Okay, so 200. Then x1 plus y1 by 4, where y1 and y1 are the long and short dimensions of the stirrup. So x1 is 200, y1 is 600, so 800 divided by 4 is again, it comes the same thing, it comes again 200, and a flat value 300 mm. Okay, so among all of this, the lowest is this, so you go ahead and give this as the spacing. Okay, so you say provide two-legged 10 mm stirrups at instead of 135, I'll give it as 130. Okay, at 130 center to center. So this is the stirrup arrangement that you are giving. Okay, so this takes care of your this takes care of everything. Top you can give some 10 mm bars as hanger. The hanger bars it should not be smaller than your stirrup. It should be at least that size. So these are my stirrups. Okay, so these are two numbers of 10. This is a two-legged 10 phi at 130 center to center. This is 4 numbers of 20 diameter bars, and of course you can draw them in the cross section as well. Okay, so of course you can draw this. So top you may give something, bottom you have your 4 numbers of 21 bars. Okay, and of course this will continue still. Diameter, 4 numbers of 20 diameter, and these are two leg stirrups at 130. Okay, so this is how you draw it. Have a look at SP34 to get more details on how to draw these things, but basically this is it. And if you want to give smaller spacing in the middle, you need to check with the torsion, because torsion is same throughout the length of the beam. It is not like your shear. Okay, shear is, your vertical shear is maximum here, 0 at the middle and maximum again at the end. But the shear caused by torsion is the same everywhere throughout the length for this case. So therefore, it's advisable to give the same setup throughout, instead of giving more at the support and less at the middle. So whenever you have torsion, most probably you have to give throughout the same number of stirrups, same spacing of stirrups. So I'll stop with this. So beams are entirely over with this. So maybe I can take some doubts on beams tomorrow and then proceed to the next part of your course.